My name is Mackenzie Rutherford. I'm an undergraduate in Miami University's Department of Geology and Environmental Earth Science program, and today I will be talking about studies regarding optical anomalies in crystals. So the goals of this are to understand the significance of studying symmetry, to understand the importance of utilizing cross-polars when looking at crystals, to know what an optical anomaly is and its mechanisms, and to recognize the importance of studying optical anomalies. But before we can discuss optical anomalies, we must understand that a crystal's growth is constrained by its symmetry, and using symmetry, crystallographers can define them into 6 crystal systems: triclinic, monoclinic, orthorhombic, tetragonal, hexagonal, and isometric. This first image is a fluorite from Tennessee that is an example of an isometric crystal. The crystal on the right is a vanadinite from Morocco and is an example of a hexagonal crystal. The optical properties we're going to be talking about are seen in thin section, which is a slice of rock that goes through a process of being made extremely thin so that light can be passed through it. We utilize a petrographic microscope to shine light through thin sections by putting them on the microscope stage. We can then look at samples through polarization using the 2 polarizers on the microscope. The lower polarizer is always used on the microscope, and when we insert the upper polarizer, we are able to see characteristics such as birefringence or interference figures, which I will talk about later. This video models the way that light travels through the polarizers. Each polarizer only allows the light parallel to their filter to pass through. The polarizers are perpendicularly oriented to one another, and as a result, no light is seen as demonstrated in this diagram. Light acts the same way when passing through an isometric crystal, as demonstrated in this animation. Because of the symmetry an isometric crystal contains, the optical behavior is the same in all directions. When no light comes through a crystal, it is known as extinction. An isometric mineral will stay extinct in all orientations. We refer to this as an optically isotropic mineral. However, when putting a non-isometric crystal in between the polarizers, the crystal alters the light passing through due to its symmetry. And that is the image that we see in the microscope. When putting that upper polarizer in, we see the crystal go extinct and then allow light to pass through every 90-degree rotation of the stage. The colors we see are known as birefringence. We can see birefringence with this quartz crystal. If you watch an individual grain, you will see that at any time it is optically homogeneous, transmitting an equal amount of light over the entire crystal. This is the behavior of a non-isometric crystal, or also known as anisotropic. Something important to keep in mind is that some minerals can have orientations aligned to look down their optic axis, making them appear isotropic. This apatite is a good example. We might be deceived and think that this apatite is an isotropic mineral. However, it is oriented along the 001, its optic axis. If you were to look along a different area of the crystal, you would get birefringence. An additional feature we can see in cross polars is an interference figure. By inserting the Murchland lens on a microscope, we can see interference figures from anisotropic minerals. The first interference figure one can see is a uniaxial figure. A crystal in the hexagonal or tetragonal system will have a uniaxial figure like the one shown here. In this animation, you can see the interference figure as the stage is rotated. The arms of the figure, referred to as the isogyres, maintain their cross formation as you rotate the stage. In the biaxial system, we see the isogyres split into 2, and with every 90-degree rotation of the stage, they reconnect. The orthorhombic, monoclinic, and triclinic crystal systems have biaxial figures. Understanding basic symmetry operations in a crystal are important to understanding what an optical anomaly is. So what is an optical anomaly? It's just as it sounds. It is a mineral that demonstrates out of the ordinary optics involving a change in symmetry. The following can cause optical anomalies: strain, post-growth ordering, and ordering during growth that results in sectoral or intersectoral zoning. The first cause we're going to evaluate is strain. External stress is the result of a crystal experiencing strain. The stress causes defects to migrate, and the bond geometry of a crystal becomes distorted. In this video, we see this with a quartz grain that should be optically homogeneous, but is displaying undulatory extinction. You can see this as different parts of the crystal go in and out of extinction. This optical characteristic reflects the crystal lattice being distorted. Comparatively, internal stress is the result of a chemical difference or damage from radiation. The chemical imbalance in a crystal creates a change in symmetry as well. Another cause can be seen with post-growth ordering. When sanidine or orthoclase, both of which have a Hermann-Mon symbol of 2/m, have silicon and aluminum atoms that order themselves into tetrahedral sites, it's indicative to the change in symmetry that we see in the crystal. A new phase, microcline, is caused by this and observed here with tartan twinning in crossed polars. This is a fluoroapatite from Ohio that displays our next cause of anomalies, sector growth. It is important to define a sector as a region of a crystal that is formed by the incorporation of atoms onto specific faces. Sectors can be distinguished through optical differences, such as color or birefringence, and chemistry. Typically, this is seen between symmetrically non-equivalent sectors, but can involve equivalent sectors when ordering is involved. Here is a similar thin section sample seen in crossed polars that allows you to see the different sectors. This apatite is oriented along the 001, just as the one I showed earlier. However, this apatite is not only allowing light to pass through, it is showing heterogeneous extinction. Each of the faces shown here are all symmetrically equivalent, but looking at this apatite in cross polars indicates that there is a difference in some sort of property between the zoned areas going extinct at different times. In this case, it is a difference in structure. This tells us that there is a lowering of symmetry in this crystal. This garnet in specular reflection shows us a feature we refer to as a growth hillock. This is an example of intersectoral zoning. Like sectoral zoning, intersectoral zoning occurs when a subsector is formed by the incorporation of atoms onto specific vicinal faces of a growth hillock. Here on the left, you can see an image of a growth hillock on the 110 face. And on the left is a sample in thin section that allows you to notice the different sectors in cross polars. Garnet, which is normally an isometric mineral, shows optically isotropic behavior. Typically, this garnet would be completely extinct in all orientations in crossed polars. However, this garnet is allowing light to pass through it at different rates. These subsectors tell us a change in symmetry has occurred in this crystal. Here's another garnet that shows the same feature from the Jeffrey mine in Canada, and here is a thin section in cross polars. As I said earlier, garnet is an isotropic mineral, so we would expect to see no light passing through this crystal in cross polars. However, not only do we see light passing through it, but it is going extinct at different times. This is also due to intersectoral zoning. A slice from this apatite crystal from the Sapo mine was taken in the area shown with dotted lines, and a thin section was made to take a closer look at its optical behavior. Upon closer inspection, it was found to be zoned both chemically and structurally. 3 different optical characteristics can be seen in this crystal. Zone 1 is oriented along the optic axis, while Zone 2 can be seen in the center with undulatory extinction, and Zone 3 has distinct subsectors. To better understand, we can take a look at the interference figures for these zones. While Zone 1 is showing the expected behavior for an apatite crystal, Zone 2 shows a strain interference figure, and Zone 3 reflects a lowering in symmetry with its biaxial figure. So why are optical anomalies important? Optical anomalies are extremely interesting because they can tell us so many things about a crystal. Zoning can tell us about the elemental composition through time, strain can tell us about what kind of environmental constraints a crystal might have gone through, and there's so many other things that optical anomalies can tell us. They tell a story about a crystal, and that might take us one step closer to understanding the Earth and its processes. Thank you for your time, everyone, and I will now be taking questions.